In our last video, we recapped some important aspects of atomic structure, and next we're going to review some basic information about compounds. So we're going to talk about the octet rule and ionic bonds, and in the next video, we'll take a look at covalent bonds. As we think about the noble gases, we know that one common feature is that all of them have full orbitals. And we also know that noble gases have a special stability. They don't tend to form compounds because they're already stable as they are. So everybody wants to be like a noble gas. Everybody wants to have this special stability. And so different elements will try to obtain full orbitals. Now, how can they do that? Different elements will gain, lose, or share electrons to be able to gain full orbitals. The two most common types of bonding would be ionic or covalent bonding. So ionic bonding, we are talking about a metal with a nonmetal, and this is where we think about a transfer of electrons. So one atom will have a positive charge and another atom will have a negative charge. With covalent bonding, this is what we see when we have a nonmetal with another nonmetal, and this is where we are sharing electrons. Whether we are considering ionic or covalent bonds, it's helpful to think about the octet rule. The octet rule basically says that everyone wants an octet. In other words, every element wants to have 8 valence electrons. And so different elements will gain, lose, or share to be able to acquire those 8 valence electrons. Now, of course, this is an overgeneralization. Some atoms can't have an octet. If we have something like hydrogen and helium, they're going to have full orbitals with only 2 electrons. When we get to larger and larger atoms, some of them can have an expanded octet. So there are, of course, exceptions to the octet rule, but still it's helpful to keep in mind if it helps to remind you about elements trying to achieve full orbitals. Let's think again about the electron configuration of one of the noble gases, neon. So neon has 10 electrons, so the electron configuration will be 1s2, 2s2, 2p6. If we look at sodium, sodium has 11 electrons. So this has an electron configuration of 1s2, 2s2, 2p6, 3s1. So it almost looks like the noble gas, except that it has one extra electron. If sodium can lose one electron, then it becomes like a noble gas. Remember, this atomic number tells us that sodium has 11 electrons, which are negatively charged, and 11 protons. But if an atom loses one electron, now it only has 10 electrons, but it still has 11 protons. So overall, this ion will have a charge of +1, and we're talking about a cation. If we look at fluorine, this has the electron configuration 1s2, 2s2, 2p5. So it's almost like the noble gas, except that it needs one more electron. And so then it will have 1s2, 2s2, 2p6. But fluorine itself has 9 electrons and 9 protons. If we have gained an electron, we now have 10 electrons, but we still have 9 protons. And so this gives us an overall charge of -1, and so fluorine will form an anion. We can think about how sodium and fluorine can come together in ionic bonding. So with ionic bonding, what we're really talking about is an attraction between opposite charges. So we have a cation attracted to an anion. This is also called Coulombic interactions or electrostatic interactions. With ionic bonding, we think about a transfer of electrons. So you can find tables of ionization energies, and that's what's required to lose an electron, and those are endothermic processes. And there's also electron affinity to gain an electron. Those are exothermic processes. When we have an ionic compound, we're going to have our sodium ions, and these are going to be attracted to our fluoride ions. So what we get is really a whole network of attraction. We're not talking about this as a specific molecule of sodium fluoride. This is a formula unit. This particular sodium ion is going to be attracted to this fluoride, and others. This sodium in the middle is attracted to all of these fluoride atoms. So we have this network of attraction. Let's take a look at another example. What if we're thinking about an ionic compound between magnesium and chloride? Well, magnesium has the electron configuration 1s2, 2s2, 2p6, 3s2. So to become like a noble gas, magnesium has to lose 2 electrons, so it will form a magnesium 2 plus cation. Chlorine, on the other hand, is 1s2, 2s2, 2p6, 3s2, 3p5. So it wants to gain 1 electron to form Cl minus. Now, when we think about the compound that forms between magnesium ions and chloride ions, we have to remember that we're going to have 1 magnesium 2 plus to every 2 Cl minus. So we're going to have 3 ions to come up with an overall neutral species. So magnesium and chlorine form magnesium chloride, which has the formula MgCl2. Let's look at a few other examples and think about what ion is going to be formed. We can write out the electron configuration, figure out whether it has to gain or lose an electron, but really we can just focus on the valence electrons. Lithium is in the first column of the periodic table, so it has 1 valence electron, so it wants to lose 1 electron to form a lithium plus cation. Bromine is in group 7, so it wants to gain 1 electron to form Br minus. Calcium is in the second column, so it will lose 2 electrons to form calcium 2 plus, and oxygen can gain 2 electrons to form O2 minus. So it's important to be able to look at a metal and a nonmetal and to easily figure out what cation or anion they form. Because next steps, you want to think about how they combine together. So if we have an ionic compound between calcium and bromine, remember that calcium forms 2 plus and bromine forms a -1. So we can think about it as if we are cross multiplying. It's going to take 2 bromines, but only 1 calcium. So CaBr2 will give us a neutral ionic compound. Lithium forms +1 cation, oxygen forms a -2 anion, so this will be Li2O. Again, lithium forms a +1, bromine forms a -1, so this will be lithium bromide. 1 lithium, 1 bromine. So the names of these compounds, magnesium chloride, calcium bromide, lithium oxide, lithium bromide, we're not specifying the numbers of the different elements, and so you need to be able to know which ions a particular metal or nonmetal forms so that you can determine the formula of a particular ionic compound. Throughout this year of organic chemistry, we are going to focus a lot more on covalent compounds, but you still need to remember the foundational information about ionic compounds so that when we are talking about different reagents, for example, you need to be able to write about and talk about the correct formula.